Hi, my name is Pothan Tang. Today I'm going to present my research on developing a relationship between ambient temperature and main tuning slide length of a standard B-flat trumpet. So how did I become interested in this project? As a trumpet player, I noticed that while trumpet players rehearse and perform indoors and outdoors, large temperature differences significantly affect the pitch. Therefore, I decided to start this project to quantify how ambient temperature affects the main tuning slide length required to produce accurate harmonic pitches, so trumpet players can adjust the instrument quickly and focus on intonation while tuning. You might ask, what is the structure of a standard B-flat trumpet like? So a standard B-flat trumpet contains three valves giving 8 different combinations of fingerings. The different pipe lengths that are created by each fingering combination allow standing waves with different frequencies to fit. Then, the mouthpiece and the bell alter the frequencies of these standing waves, allowing the entire chromatic scale to be produced on the trumpets. How might temperature affect pitch? Let me explain. As the ambient temperature increases, the frequency of sound waves increases. Pulling out the main tuning slide increases the total pipe length of the trumpets, in order to allow standing waves with longer wavelengths and lower frequencies to fit in. Conversely, when ambient temperature decreases, the frequency of the sound waves increases, and the main tuning slide should be pushed in. Therefore, the main tuning slide length put out should vary directly with ambient temperature. Here is a schematic of the experimental setup used in this experiment. A standard Bach B-flat trumpet with Bach 3C mouthpiece was being played on. 5 thermometers with probe rotates to the respective locations on the trumpets to measure the temperature distribution. A 6th thermometer was set on the side to measure the ambient temperature, with the probe suspended in the air. 3 paper rulers rotate to the tuning slides to measure their lengths. A clip-on tuner was clipped to the bell of the trumpet to measure pitch accuracy, and a timer was used to keep track of the playing time during each experimental trial. After all the data collection, what relationships did I investigate in the data analysis process? I investigated the location on the trumpet versus the temperature, the playing time versus temperature distribution, the notes on the chromatic scale versus the total tuning slide length, and finally the temperature distribution versus the main tuning slide length. Since the measurement of ambient temperature was most practical to a trumpet player, and it had a clear relationship with the main tuning slide length put out, I chose to precisely quantify this relationship using regression analysis. Here is what I found. I found that an exponential regression model had the highest correlation, and suits the hypothesis that the main tuning slide length put out varies directly with temperature. On the graph of the model, error bars were drawn for each data point, representing the 2 degrees Fahrenheit error of temperature measurements and 0.05 centimeters error of length measurements. Based on this model, a table of values with ambient temperatures and also their corresponding main tuning slide lengths put out were generated. What are some sources of error in this experiment? A potential source of error was the pitch fluctuation produced by the embouchure. If the air stream blown through the mouthpiece was not constant, both the sound intensity and the pitch would fluctuate. If there was excessive tension in the lips, the resulting sound would not be resonant, and the resulting pitch would deviate from the frequency of a standing wave. What are the limitations of this experiment? Without access to a controlled temperature chamber with a wide range of temperatures, the performed experiments were limited to ambient temperatures controlled by air conditioning, location, the time of the day, and the weather. Also, without access to different trumpet players, the experiments were performed and data was collected from a single trumpet player, which was me. However, even if trumpet players differ in playing technique, they can find a similar exponential relationship through experimentation to describe their trumpet playing, because the underlying physics is the same. So how can trumpet players utilize a mathematical relationship like the one shown previously? First, they can warm up for 5 to 10 minutes to establish a steady temperature inside their trumpets. Secondly, they can obtain an approximation of the ambient temperature. Thirdly, they can pull out the main tuning slide according to the length suggested by the relationship. Then, they can attach a tuner on the bell of the trumpets and sustain the tenor C notes. The tuner should indicate that the pitch is close to being in tune. Finally, they can make additional adjustments as needed, as long as the ambient temperature stays steady and the trumpet is constantly being played on. The length of the main tuning slide will produce an accurate pitch. You might still wonder, is the relationship developed in this research applicable to other brass instruments? The answer is yes, because they are all made of the same metal. The specific relationship parameters may differ for different instrument designs, but all brass metal will respond the same to temperature. Therefore, this research may inspire other brass instrument players who tune by adjusting their tuning slide lengths to develop similar relationships for their instruments. Here are the image citations used on this slideshow. Finally, if you are interested in my research, you can access the preprints of my paper on the Research Archive of Rising Scholars using this QR code. I hope you enjoyed my presentation, and thank you very much for listening.